Greetings everyone. Today we are presenting our CSE 106 mini project. I am Miftahul Adon and with me are my group members Muhammad Zubair Firdaus and Sumaya. Our project is divided into two parts. In this presentation, we will walk you through the two parts of our project. Part A, empirical time complexity of linear search. Part B, friendship graph using indirect graphs. Linear search. Let's begin with part A, the empirical study of linear search. The main objective was to test the average case performance of linear search and see how closely it follows the theoretical complexity of ON. To achieve this, we implemented linear search in Python, used arrays of size ranging from 10 to the power 4 to 5 into 10 to the power 4, performed 1000 random searches for each array size, recorded the average time for each case and compared it to theory. So essentially, the problem was, does practice match theory? Empirical results of linear search. Now, let's talk about the graph. The plot we obtained showed a steady linear growth in search time as the array size increased. This confirmed that the empirical results followed the theoretical ON time complexity. In other words, as the number of elements doubles, the average search time also roughly doubles. This agreement between theory and practice highlights the predictability of algorithmic analysis. Methodology. Linear search. Here's how we conducted the experiment. We generated random arrays of increasing sizes 10,000, 20,000 up to 50,000 elements. For each size, we performed 1,000 random searches, ensuring fairness by averaging the times. The tools we used included Python for coding, NumPy for array handling, and Matplotlib for plotting our results. This systematic approach allowed us to measure performance trends accurately. Linear search source code. This slide shows the Python source code for linear search and data collection. It's a straightforward implementation, but the important part is that the experiment was repeatable and the code ensured fairness by averaging over 1,000 searches per array size. The simplicity of the code also makes it easy to extend the experiment for longer datasets in the future. Now we are going to talk about B1 problem statement, which is friendship graph. Moving on to B part, the undirected friendship graph. This idea here was to simulate a social network. In this model, each user is represented as a vertex. Each friendship is represented as an edge between two vertices. The tasks were computer vertex degrees or the number of friends per user. Verify the handshaking theorem, which states that the sum of degrees of all vertices equals twice the number of edges. And finally, determine the number of connected components in the graph. Results of undirected friendship graph. The results here shows that as the number of vertices increases, the network tends to become more connected. In smaller graphs, there are often many separate components. But as the number of vertices grows, most nodes end up belonging to one large connected component. We also verified the handshaking theorem successfully, which confirmed the correctness of our implementation. This experiment illustrates how real-world social networks behave. Larger networks tend to be more connected. Methodology, friendship graph. To simulate this, we used an adjacency matrix representation for efficiency. We created random graphs with different network sizes, 500, 1000, 1500, 2000, and 2500 users. Friendships were randomly assigned, but they were always bidirectional, meaning if A is friends with B and then B is friends with A. We then used Python to compute the number of connected components, which essentially tells us how many separate groups of users exist in this network. Undirected friendship graph source code. Here, we see the Python code used to generate the random undirect graph, calculate degrees, and find connected components using DFS function. Just like in the first part, the implementation ensured correctness and repeatability. The key takeaway is that the simple code can still provide powerful insights when combined with systematic testing. To wrap up, in conclusion, in part A, our linear search experiment confirmed the theoretical time complexity of ON. The experimental results matched our expectations. In part B, our friendship graph experiment showed that the handshaking theorem holds true and larger graphs naturally form fewer